Welcome, my dear students and YouTube viewers, to Chapter 4. In this video, I will discuss and teach you solvents, solutes, and electrolytes. So after this chapter, not just this video, but all of my Chapter 4 videos that will ensue, you should gain the following skills. In other words, after this chapter, you should be able to define the terms solvent, solute, electrolyte, and non-electrolyte. Use the solubility rules that we will describe in this chapter to determine if different compounds are soluble or insoluble in water. Identify the precipitates that form in precipitation reactions. Write a net ionic equation. And memorize the names and formulas of specific strong acids and strong bases. In addition to that, you will also be able to write chemical equations for neutralization reactions, determine compounds' oxidation numbers, write chemical equations for reduction oxidation, also called redox reactions, calculate an aqueous solution's molarity and concentration, then use this molarity to calculate grams of a solute. You will also be able to explain how to prepare aqueous solutions with specified molarities and use mass relations to do calculations involving titration reactions. So let's get started. According to a quote taken directly from my suggested text for this class, which is this one referenced down at the bottom of this slide, a solution is a homogeneous mixture of two or more substances. The substance present in the greatest amount is called the solvent, and the other substance or substances are called solutes. They are said to be dissolved in the solvent. When a small amount of sodium chloride, NaCl or table salt for example, is dissolved in a large quantity of water, water is the solvent and sodium chloride is the solute. Pictorially then, you can imagine a solid, such as table salt or something represented here, being added to a liquid. Now, if the liquid is added in a larger amount and the solid molecules or atoms start to separate out inside the liquid and disperse among them, then we call this a solution. It is a homogeneous, that is evenly distributed mixture of a solute and a solvent, where the solvent is the major component in solution and the solute is the minor component in solution. So what is an electrolyte and non-electrolyte? Well, a water-soluble substance like sodium chloride table salt that releases ions when it dissolves in water is called an electrolyte. Now, in order to be an electrolyte, a substance must be an ionic compound. That is, its chemical formula must contain both metals and nonmetals. And by way of reminder, this table shows us which elements are metals and nonmetals. For now, we'll just ignore the metalloids. Second, in order to be an electrolyte, a substance must be water soluble. That is, it has to dissolve in water, which we will discuss later on in this chapter. In contrast, though, a substance such as sucrose, which is table sugar and has this formula, you'll notice that this formula does not have any metals in it. So it's a molecular compound. So in other words, a substance like sucrose or table sugar that does not form ions, and it obviously doesn't because it's not an ionic compound, when it dissolves in water is called a non-electrolyte. Now, a non-electrolyte is any substance that fails to meet either rule number 1 here or rule number 2 or both. So why does water have the ability to dissolve ionic compounds? Well, as it turns out, oxygen is more electronegative. That is, it's more electron greedy than hydrogen, which means that H2O molecules, oxygen atoms, hog electrons away from the hydrogen atoms. So water's oxygen atoms end up with a partial negative charge represented by this little symbol here, while their hydrogen atoms end up with partial positive charges. As you probably know from your vast experience, I'm sure, playing with magnets, pluses and minuses are attracted to each other. And the same ends up being true for molecules and atoms. Now, this means then that water readily dissolves many ionic compounds because ionic compounds include positively charged cations and negatively charged anions. Now, this dissolving, the process of something dissolving in a solvent, is called solvation, eternal solvation. No, I'm just kidding. It's just called regular solvation. I just love to say that. Anyway, so molecular compounds, that is compounds that contain all nonmetals, do not separate into cations and anions in water. You can see, for example, we take sodium chloride crystals and throw them into water. What happens? Well, in sodium chloride, as you know, there is a sodium cation with a strong plus charge and a chloride anion with a strong minus charge. When those things hit the water molecules, they get attracted to the complementary opposite charges in the water molecules. In this case, the chloride anions are going to be strongly attracted to the partial plus hydrogen atoms in water, and so those chlorides will be kind of clustered around by water molecules pointing their partial positively charged hydrogen atoms at the chlorides, whereas the positively charged sodium cations will be attracted to the partially negatively charged water anions on these oxygens, right? So those oxygens will cluster in the opposite way, complementarily to the sodium cations, again just like magnets. This allows the sodium and chloride ions to be drawn apart from each other by the water molecules. Again, you can see the partially positively charged hydrogen atoms are pointing complementarily to the negatively charged chlorides, just like magnets. Opposites attract. And the partially negatively charged oxygens are pointing at the partially positively charged sodium cations. And that explains why sodium chloride, as well as many other ionic substances, get dissolved so readily in water. So you might ask, why do some molecular compounds dissolve in water then? Well, let's take, for example, ethanol. Ethanol that has this formula also dissolves readily in water. It does not, however, form ions. So why does it dissolve in water? Well, again, we have a bunch of water molecules with their partial pluses and minuses. I'm not drawing here, but you can sort of imagine them based on what I just showed you. Ethanol molecules also have partial pluses and minuses on their hydrogen and oxygen specifically, or most particularly. Partial negative on the oxygens, partial positives on the hydrogens here. So, like magnets, they will point toward the opposite complementary charges in the water molecules, which allows them to dissolve as well. So ethanol also dissolves, and other molecular compounds, not all, but some also dissolve as well, but they do so with their partial plus and partial minus pointing at the partial minus and partial plus in the water molecules complementarily, but in opposite fashion like magnets. This allows them to disperse and dissolve inside the water solvent. The difference, of course, between molecular compounds that dissolve in water and ionic compounds is that ionic compounds have true cations and anions that separate completely out when they dissolve in the water, whereas molecular compounds that dissolve in water only have partial negative and positive charges. Does that distinction make sense? Good. I end then with one beautiful tip. In general, for molecular compounds, compounds whose formulas contain all nonmetals, the more carbons and hydrogens the molecule has in its formula, the less water-soluble it is. And the more OHs in its formula, the more water-soluble it is.